wrong button. These buttons are bigger. I'm the worst cell phone person. I spell things wrong all the time. My fingers are too big for the buttons. These are better. You might mess that up.
Now watch, you want to see something? You want to see a shortcut? You guys like shortcuts. You guys always try to take shortcuts. Don't always take the shortcut. There's value to going through and doing it this way. There's value. You get a good understanding. Miss, make. Okay? But I'm going to show you the shortcut. I'm going to show you the shortcut. It's going to come up over here. Okay? The old calculator. Ready? We can do this. We're looking for one thing. One thing. Okay? The seventh shot. We can do this with what's called GeoMet. Let me see this. I call it GeoCDF, but it's GeoMet PDF. We're looking for one. We are looking for one. Okay, here we go. Ready? So you go to the second dister again. You go way down underneath the binomial. There's something called Poisson. Poisson is not covered in AP statistics, so we won't talk about it. But underneath that, there's CDF and PDF. We're doing PDF right now. Hit enter. Put in 0.15 for your probability. Put your X value as 7. Oh man. Oh snap. Look at that. Same answer. Okay? And you're going to say, well, why do you show us this way if we get the same answer with a calculator? Because you could type something in the calculator and type it in wrong and hit a wrong button. And you have no idea if you're right. This, I know, that's easy. You failed 6 times. If it's a quiz or a test, I'm going to take the time to do that out, rather than just type it into a calculator and be done with it in a second, not know if it's right or not. All right? So, what's the probability that the first shot is made within the first 7 shots? So, for this, what I want you to do is, okay, what I want you to do is try to write that as an inequality. Okay? Try to write that as an inequality. Write it as an inequality. And then we're going to break it down. We're going to figure out how to do it. We're going to figure out how to do it. We are. Okay? So within the first 7 shots, that's the probability of X what? Is it greater than or equal to? Is it less than or equal to? Is it greater than? Is it less than? I don't know. I don't know. We're going to have to figure it out. What do you think? Within the first 7 shots. So, is 6 an answer to that? Yes. Is 8 an answer for that? No. So probability that X is less than or equal to 7. So, we could do that as the probability that X equals 1, plus the probability that X equals 2, plus the probability that X equals all the way to 6, right? Or all the way to 7, excuse me. All the way to 7. You could add all those probabilities up. Or we can use the old GeoCDF, okay? GeoCDF, and add all those numbers up and see what you get. Okay, ready? We go here. We do second vars for dister. GeoCDF, 0.15, 7, and I get 0.679. 0.679. All right? Make sense? All right. We're almost done. We're almost done. Trust me, I've been doing 6 sections, 6-3, all morning. All morning. Okay, it's now 11 something. I took some breaks, I did some other stuff. I wasn't talking the whole time. So we're going to go through and talk about this, and we're going to do a few examples. The examples are easy. It's using 2 easy formulas. Relax. So, This table shows the probability distribution of y, the number of picks it takes to match the lucky day. We can't show the entire distribution because the number of trials it takes to get the first success could be a very large number. So if you're finding the first success, you don't know what that last number is. It's not fixed, okay? So they're showing you a partial list, partial list, okay? Whenever you're doing a histogram of a geometric distribution, it is always going to be skewed to the right, okay? So if your probability is like, say, 0.15, like the free throw one, okay? And you do it in the first try, what do you get? Well, you get 0.15. And then the next one's going to be 0.15 times 0.85, right? So you missed, well, the other order technically. 0.85 times 0.15. If you're going to make your first free throw on the second shot, it means you missed the first one and then you made the second one. So they're all going to go, these are going to go down, okay? No matter, you know, however you do that distribution. So it's always going to be skewed to the right. The shape is always skewed to the right, okay? And because you're multiplying by a fraction each time, okay? This one, the next one will be 0.85 times 0.85 times 0.15. So again, when you multiply by a number less than 1, the math tells you it's going to go down each time. So it's skewed to the right. The center, the mean is 1 divided by the probability. We've talked about that already. The variability, we use the standard deviation. Okay, now this I want you to see. I want you to look at this and I want to explain it because there's a pretty considerable difference if you make a mistake with this. Okay? Mathematically, this is not equal to this. Okay? I want you to look at those. I want you to look at those and tell me and say out loud what you think the difference is. What is the difference between those two things? What is the difference between these two things? Well, this one, we're taking the square root of this and dividing that by p. Here, we're doing all of this and taking the square root. It's not the same. This is the formula. And if you look, the fraction bar goes over the whole thing. So you have to know that these two things are not the same. And this is what we're doing. Okay? This is how we do it, baby. All right? That's it, right there. So we're going to look at a couple examples. And that's how we finish. That is how we finish. So, Benford's law again. Benford's law. Okay? And I'm going to let you not interpret this one, because Benford's law, we hate Benford's law. We're so sick of Benford's law. Why they use that as a primary example in chapter 6, I don't know. So I'm not going to make you interpret that, but we are going to interpret the next one. Okay? The mean. Well, our probability here is 0.097. Okay? So the formula said the mean of, what is this, Benford's law? So we'll say the mean of B is equal to 1 divided by 0.097. 1 divided by 0.097. Let's look at that. 1 divided by 0.097 gives me 10.31. Here's my mean. Now, standard deviation of B. Square root, 1 minus 0.097. Take that whole thing and divide by 0.097. I'm going to show you why it's different from the other thing we're talking about. So 1 minus 0.097 is 0.903. Okay, so this is going to be the square root of 0.903, and then dividing that by 0.097. So the square root of 0.903, let's do that. Second square, 0.903 gives me 0.950. And then I divide that by 0.097. Divided by 0.097, I get 9.796. So I'm going to make it 9.8. Okay? And I want to show you that if I did it the other way, if I did this, 1 minus 0.097 divided by 0.097, this is wrong, okay, but I'm showing you that. this 0.903 divided by 0.9097, and then taking the square root. 0.903 divided by 0.097, 9.3, and then taking the square root of that. It's going to be 3 point something, right? Second square root, 9.31, 3.05. Wrong, wrong, wrong. Okay, you got to do it this way. You got to do it that way. So, do the next two problems. That'll finish 6-3. The marathon that is 6-3. Marty playing roulette. Remember what I told you about roulette? Remember what I told you about craps, blackjack, slot machines. It's all the same. They are there to take your money. You do not win in the long run. You guys are now statisticians, okay? Novice statisticians. At the end, you'll be expert statisticians. You should know that the math doesn't add up. Okay, gambling doesn't win in the long run. MGM doesn't stay open. Pay their employees health insurance, pay all the electricity because they're giving away money. Do it. I think you can interpret this one too. Hope you got this one. Dividing is the same as multiplying by the reciprocal, so this should be 38. 38 rolls. Okay, so, or spins, we're talking roulette. If you play many, many games, the average number of games that you would need to play for that ball to land in the 15 spot would be 38 games. Okay? Standard deviation. Doing that math out, you should get 37.497. We have to interpret that. So if you play many, many games, the number of games it will take for the ball to land in the 15 spot will vary by 37.497 games from the mean, which was 38. And that is section 6.3.